Morning everyone, I'm Rocky. I'm going to tell you about RLLAB, a reinforcement learning framework. So it has been originally developed at UC Berkeley and now continues to be maintained at both UC Berkeley and OpenAI. And this is joint work with my colleagues, Peter Chen, Brain John Schumann, and Peter Gibb. So Chelsea just gave like a wonderful motivation for DeepRL, so I won't repeat that. So I'll jump directly to what does RLLAB offer. So in a quick summary, it is a collection of very diverse and challenging implementations of different RL environments in simulation, and a set of very modular, easy to use, and highly parallelized algorithm implementations. And finally, some very convenient tools for running experiments on the cluster and visualizing results, and splitting the results into different hyperparameters. So next I will introduce each of those components separately. So first, let's look at the environments. In summary, we offer a wide categories of environments, including many environments in the classical reinforcement literature, some locomotion environments, some environments that require memory, and finally some environments that might require some hierarchical skills. So first, for the classic environments, we have like very classical textbook example like tugboat balancing and acrobat, also known as double pendulum, or mountain car, or double inverted pendulum. So those tasks are very low dimensional, and sometimes they can even be solved with calculated methods, but they already highlight some of the challenges encountered in reinforcement learning. For example, in mountain car, you have to, it is a very tricky exploration problem because there are local optima until you actually hit the hill on the mountain. So, and moving beyond that, we have locomotion environments, which are much higher dimensional, and it ranges from 3 degrees of freedom to 28 degrees of freedom in the most challenging class, which is the full humanoid. So those tasks focus on very diverse locomotion skills, where across the environments, the goal is to simply move forward as quickly as possible. And all of them are implemented in the Joko basic simulator. So next, we have a set of partially observable environments, which are built on top of the classic environments that we saw before. And so basically the idea here is that we will either restrict the amount of information you get per time step, or if you have a very noisy observation, or you vary the underlying physics parameters of the dynamics model, in which case, in all of those situations, you have to integrate over your past observation to get a more accurate estimate of your current situation. And finally, there are some hierarchical environments, which are some mixture of the locomotion environments we saw earlier, placed into a larger scenario. So on the left, we have, say, either an ant or a swimmer in the simple food gathering task, where you have to collect all the green balls and avoid the red balls, and you only get rewarded when you hit one of the balls. So it's a very sparse reward problem. On the right, we have a simple maze, and so again, we have either the swimmer or the ant, which needs to navigate to a target. Here, the target is to the other corner. And again, you only get a reward when you actually hit the goal, so the reward is very sparse. So what does the program interface look like? It is extremely simple to use those environments. So I took the carpool environment as an example, but you can replace it with any other environment, and the usage is exactly the same. And the core interface is just 2 functions. One is reset, where you reset the state of the environment to one of the initial states, and the other is step, where it takes an action that is computed by your policy, or you can just take a random action as shown here, and then it returns the next observation you get, the reward you receive from the environment, and the flag, which tells you whether the environment is finished. And finally, you can optionally render the environment to visualize what's actually going on. So since the release of RLLAB, OpenAI has released yet another framework called GIM, which is a much larger collection of environments. So it includes like environments like Atari, and also absorb many environments in RLLAB, like the locomotion environments. So the good news is that you can seamlessly use all the environments in GIM using the same interface in RLLAB. And all you need is just like a simple wrapper called Jimmy, followed by the ID of the environment in OpenAI, and the rest of it follows the same. Okay, so next let's look at some of the algorithm implementations. So currently our lab focuses on algorithms that work with continuous action spaces. And as a result, it mostly focuses on policy gradient-based algorithms. And some of the gradient-free algorithms such as CM, CMA, ES. And the algorithms noted in bold are the more commonly used ones, like the raw policy gradient algorithm, also called reinforced or vanilla policy gradient. And also some of the trust region methods, such as trust region policy optimization, abbreviated TRPO. And finally, there's an algorithm from DeepMind called DDPG, which is an actor-critic algorithm. So in implementing those algorithms, we noted that there's a lot of commonalities shared among them. For example, many of the algorithms are batch-based, which means that you use the policy to collect a lot of trajectories, and you use that to make an update to your policy. And also, many of those algorithms use a baseline to reduce variance in your gradient estimate. And finally, many of those algorithms are gradient-based, so they can benefit from using an automated differentiation library. So in implementing those algorithms, we try to share as much components as possible. So as an example of that, let's look at this simple code snippet, which runs the TRPO algorithm on Hyperparameter. So it's very standard. You construct an environment you want to use. And here I use a very simple fully connected neural network as the policy with a Gaussian action as the output. And also I use a linear baseline to reduce variance in your gradient estimate. And then you can basically construct the algorithm and then run it. So so now the question is, what if you want to make some changes to how you use this algorithm? So if you want to swap it to another environment, it's very simple. You just change the environment, and you don't need to touch anywhere else. You can also use a different policy, like a recurrent policy. In this example, is using a get recurrent unit. You can also change it to use a different baseline, or you can even change it to a different algorithm, like the vanilla policy gradient, without touching anywhere else. And finally, all the algorithm and policy implementations are available in both Diano and TensorFlow. Okay, cool. So finally, let's look at some of the experiment utilities that our lab offers. So first, if you work in deep RL, you probably know that you need to tune some hyperparameters to get the best performance. So we also know that, and as a result, we offer some functionalities to run experiments on the Amazon EC2. And you only need to make very minimal change to your experiment code. So on the left is what you usually write, and on the right is what you need to write to launch it remotely. So you basically just wrap your code in a function call, and then you call some other method, which will serialize this function call and upload it to the remote end, and then it'll download all your local code, and then execute it, and then it'll upload all the results onto S3. So I'll skip this this procedure. So this is an example of a simple hyperparameter search. So here I'm trying to tune the step size of an algorithm here, TRPO. So I just have a simple for loop which loops through some step size options. And to get more robust results, I also use some different Cs. And then I just call this run experiment light function, and it'll launch, in this case, 15 jobs in total onto EC2 all in parallel. We also offer some simple functionalities if you have more complicated hyperparameter needs. So like if you have, say, 10 different hyperparameters, hopefully you don't need that. You don't need to like write nested for loop with 10 indentations. You can just use this class called variant generator, which also supports more complicated logic like dependency among different hyperparameters. So we also offer a visualization toolkit, and I'll try to live demo it. So this visualization basically shows the result of the 15 experiments that I ran earlier. And so you can basically point it to a folder of all the logs, and you'll launch a web server locally. And this is what you get. So you can look at all the learning curves across iterations, and you can change different attributes that you want to display. So here I'm displaying the average episodic return that you get. But you can also change it to say display the entropy of the policy and see how it changes. And or some say, what about the tail divergence of your policy? And you can split it by the step size, which I tune, and you can also change it to any other hyperparameters if you have them. And you can also look at individual runs, or you can have different number of figures. So like we can build them by step size and look at all the curves. And you can do some simple filtering, say only look at results for step size 0.01. Okay, this is just in case the lab demo failed. So who's using RLLAB? So as of yesterday, we have over 700 stars on GitHub and over 200 forks. And there has been about 50 citations of RLLAB since we only encouraged instead of forced them to cite it. Like the actual number of people using it might be higher. And many of them are outside OpenAI or Berkeley. So I will also talk about some of our own work built on top of RLLAB. So the most recent work is one-shot imitation learning, where we consider a meta-learning setting where your policy will receive a demonstration of the task that you want to achieve, and also the current state, and output the action you want to take in this new situation. So here on the left, I'm showing a demonstration of some task of stacking blocks into some configuration. On the right is the policy reproducing the same goal on a new configuration, and it uses some intention mechanism. So the bottom side shows the tension max of the policy in operation. So an earlier work considers meta-learning in a reinforcement learning setting, where instead of the normal RL, you have a fixed MDP. Here we consider the policy dealing with a distribution over MDPs. So in this example, the distribution can be a collection of different phases. And the policy is allowed to interact with the environment for multiple episodes, and it receives the reward from the environment. So if you train it, it can effectively act as a very efficient RL algorithm by itself. So we also did some work on adversarial attacks in reinforcement learning. So this is a policy trained using TRPO. So by the way, it also works with Atari. And you can adversarially perturb the input to the policy. And on the leftmost, hopefully it's not too small, your pawn pair is performing very good. But as soon as you make some very infinitesimal perturbations, then it completely screwed up. And we also did some work to try to tackle some of the hierarchical environments. So in this example, we consider using stochastic neural networks to learn skills in a pre-training environment, and then apply them in some of the challenging tasks like maze. And also we consider exploration bonuses to speed up learning, like in this example using simple count-based bonus, which turns out to be very effective even on high-dimensional state spaces. So we also consider exploration bonus based on maintaining a distribution over your neural network weights of a dynamics model, which you'll learn over time, and measure the surprise in that distribution to give you exploration bonus, which turns out to be pretty effective in this full gather environment, even with very sparse rewards. So, and finally, it turns out that experiment utilities that we provide can also be used outside RL. So, hey, on supervised learning. So you can also use it to launch experiments and make it super neat. Okay, so there has been a lot of other deep RL libraries that are released, most of them after RLLAB. So to be honest, I haven't used all of them, so I encourage you to check them out. Although I'm pretty confident that RLLAB is one of the best in terms of its modular design and its inclusive components like all of the experimentalities that it offers. So some future directions. So we apparently want to add more support for algorithms, especially those that support these reactions, like probability-based algorithms. But more importantly, we think that we need to look beyond the standard RL paradigm. So there are many interesting paradigms that are not considered in the standard MDP setting. For example, just imitation learning, where you are not just interacting with the environment by yourself, but you actually have some demonstrations. And there's also unsupervised learning combined with RL, which is pretty unexplored, but I think it's very important. And there are also adversarial games like Go, which doesn't really fit into the normal MDP setting. And meta-learning, where instead of having a single environment, you have a distribution over them. And finally, multi-agent learning, where you might extend beyond 2 agents and have, say, many agents interacting with themselves. Okay, and yeah, it's okay to take some questions.
Can you maybe talk a little bit more about like what your type of multi-agent learning?
So I don't have any personal plans, to be honest. I think it'll more be driven from needs from the researchers that are actually working on multi-agent, and then we will see like what is the best interface moving forward.
Okay, so yeah, we also we've used RLLAB for doing multi-agent stuff. Actually, it's one of the questions that we've been trying to figure out, like what the best way to interface with it.
I see. Yeah, then we can definitely talk about it more.